Welcome to the 29th class on operating system and Linux. I'm Manibhushan D'Souza, and in today's class we are going to look at virtual memory. In particular, we are going to look at demand paging. So let's start the basic idea of virtual memory. Now, what is virtual memory? A virtual memory is a technique wherein we allow a program which is larger than the physical memory to get executed. What do I mean by saying that? Now we know that whenever we write a program, the length of the program could be anything. And you know very well the capacity of the disk is much larger than the capacity of the RAM. Now just assume that you have a RAM this size and you have a program which is much larger than the existing RAM. In other words, the size of the program is larger than the available memory. So I can't fully fit the program into the memory. So if virtual memory was not there, then such a program can't be executed because the entire program cannot be fitted into the memory. Okay, so it's like let's assume that you have written some commercial application, very large application, and the size of it is very large. So in that case, what happens is it will go beyond the limits of your RAM or the memory which is there on the system, and because the program is larger, it cannot be fitted into the memory. And we know very well that if the program does not reside on the memory, it cannot be given to the CPU for execution. So I cannot give a program, or in other words, if the CPU, okay, if the program does not fit into the memory, I cannot give that thing to the CPU. So how do we deal with that? To deal with that, we have virtual memory. So virtual memory is a technique wherein we try to run a program, or we try to execute a process that is not completely fitted into the memory. Okay, so how can we achieve that thing? So if I don't have the RAM with me, then I have to somehow extract this particular thing. This is not really available. I have to virtually create that much of space. So my program requires this much of RAM which is not there. I have only up to here I have the RAM. But what about the remaining RAM? Remaining RAM I am creating as a virtual. Okay, so what's the advantage there? With the virtual memory, you can in fact create a very large amount of memory. So if you have, just to give you an example, if you have 1K of RAM, so what is 1K of RAM? 1 kilobyte of RAM. You can say to a program which is 1 MB, remember what's the difference? 1024 is the difference. So I can load a 1 MB program into that. Remember, so even though I have 1 KB of RAM, I can load 1 MB of a program. Now, how it is possible? Now you may ask that. How can you do that? This is 1024 times larger. How can you load something which is 1024 larger than the existing RAM? For that we use the technique called as virtual memory. Okay, so let's look at how the virtual memory really works. Now we know that we have studied about paging. So what is the idea of paging? You divide your program into pages. So you divide your program into smaller unit called as the page. So this is your full program. So whatever you have written, very large program, you divide it into smaller groups called as page. Okay, this is the idea that you have. Now what you need to do, somehow your program has to be fitted into the memory. So when your program is executing, okay, your program will say that I want to read from the page number 0. So I want to read from the page number 0. Then what you have to do, your program, you know very well, your program resides on the disk. You take that part, that is page 0, then try to load it in the physical memory. So this is the idea of a paging, you know very well. So in paging, what you do is you divide your program into very large unit, into a smaller unit, large program into a smaller unit, and then you load, they are called as the pages, you load those pages into frames into the memory. So this is the idea that you are all familiar with. Now the problem here is your size of your program is very large. This is very large, but the size of your memory is small. How can I load the program in that case? So when your program wants page 0, the page 0 may be available here, page 1 may be available here. This is your physical memory. Let me tell you, this is the virtual address that we are creating. This is page 3 and so on and so forth. Now this may be page n. What if your program says I want to read n plus 1? If your program says I want to read the page number n plus 1, your physical memory is already filled. So where will you fit the n plus 1 now? So that's the problem. Hope you get the problem. So you have filled all the units, the entire physical memory is filled. Now your program says I want n plus 1, n plus 2, n plus 3 and so on and so forth. I want all these pages to be brought into the memory, but the memory is already full. In that case, what you are going to do? So in this case, what you do is you don't directly go into the physical memory. You map those physical memory elsewhere. So this is the idea that you have. So you create a mapping. So what do you mean by saying mapping? Now remember, when your program is running, you may not need entire program. The full program may not be required. Just to give you an example, suppose your program is running a while loop. So while I less than 50, suppose say you are running a program and you have some set of code here. Okay. Now you know very well the entire program will just fluctuate inside this while loop forever. Whatever the instructions which are written outside the while loop, either at the top or at the bottom, they may not be required as long as you are inside the while loop. So in other words, what do I mean to say is, when this block is getting executed, not all the blocks are required. You don't require the entire program to be there in the memory when you are executing one block. To make it still more clearer, when you are executing the program in the page number 2, page number 0 may not be required. I don't say that it is not required, it may not be required. Page number n may not be required. Okay? Not that it is not required. I'm not saying definitely I can't say, but generally it is not required. So this is called as locality of reference. What do I mean by saying locality of reference is, if the code in this section is executed, generally what we expect is the next code or the next variable or whatever it is will be executed. So within this neighborhood, that is called as a locality, the program will run within that particular locality. If you have the instruction within that locality, that's enough. You don't require the first part of the program, you don't require the last part of the program. Generally, not always. There may be required. Somebody may write a go-to statement and simply jump to the first and last part. That's a different issue altogether, but generally it won't happen. So generally the code will exist within its locality. That's called as locality of reference. So why did I say that thing? Now suppose the page n is loaded. So page n is loaded somewhere here. Okay, page n is there. Now I told you that entire program, page 1 may be here and so on and so forth. The entire memory is full. When you load the page 0 has come here, page 1 has come here, page 2 has come here, page n has come here. Now somebody is asking me or the program is asking me, okay, give me n plus 1 page. So in that case, entire memory is full now. Physical memory is already full. What to do in this case? Now just search which one is not really required. If you find that this place, that code is not really required because you are there at the nth place. Remember, you are there at the nth. The beginning of the program may not be required. Because I have told you here, if you look at here, you are in the while loop, the other part may not be required. So you can select any one of this page and replace it with that n plus 1. So what you are doing, so your program has asked you for a, so your program has asked you for n plus 1 page. And what you know that your n plus 1 page is here. So you notice that somewhere here one page is not really required. So you bring that n plus 1 page. So you bring that n plus 1 here, place it here. Okay, replace. In other words, you replace it and make an entry in your mapping table saying that this entry, the number 2, let me say this is number 1, physical address 1, physical address 2. Physical address 2 has the page number n plus 1. Okay, so when your program says give me n plus 1 page, you just go here, go to this location and then start reading it. So it is simple as that. If n plus 2 is required, if your code says I want n plus 5, I want the n plus 5 page to be brought in, search any page. Okay, this is free, or if this is not being used, bring that page n plus 5, make an appropriate marking saying that this particular location, the page number n plus 5 is available. So when your code is asking you for okay, give me the n plus 5, okay, you say okay, go here, go to this location, go to this location and then start reading it. So in other words, wherever your program makes a reference beyond the physical memory, you just bring that page and replace somewhere and just put it there. So that's the idea of creating virtual memory. Hope you get that idea. Okay, what's the advantage of doing this? One of the advantage, definitely you can load a program which is larger than the physical memory. Remember, you are not loading the entire program, you are loading only part that is required. So is there any problem with the CPU? There is no problem. Remember, CPU will never ask any program that I want your entire code. CPU just knows something called as program counter. I think I have already told you there is something called as PC. What is this PC? There is a register inside CPU called as PC. That is program counter. What does the program counter will do? It will tell you, or it will point you to the next instruction. That's all. Next instruction to be loaded. Now whether that next instruction is there or not, CPU will not ask that. You tell the CPU that all the instructions are there. You tell me the address, I will give you. So you want n plus 1th page, I will give you. So just wait, I will load it and give it to you. You want n plus 50th page, I will load and give it to you. So CPU is very happy saying that CPU says that is your problem. You manage your memory on your own. Whenever I ask for the instruction, you just give me the instruction. How you get that instruction? In the page you get it, in the frame you get it, in basket you get it, in a plastic polythene bag you get it. That is not my problem. When I ask for an instruction, you just give me an instruction. So as long as CPU is happy, your program will definitely get executed. So now let's come back to the benefit over here. What's the benefit? Benefit is you can always load a program which is larger than the physical memory. Otherwise, what will happen? Without the virtual memory, you would have had a restriction on the size of the program. So as a programmer, suppose if you want to build a program, then there is always a restriction. Your program cannot go beyond that. So in when you write your English paper, that is the answer. So write an essay not beyond 200 words, not beyond 300 words. Sometimes they give you an essay like that. Write an essay on Indian Constitution or Indian independence, not beyond 250 words. So you are restricted 250. You can't go beyond. In the same way, here you say write a program for so on so forth, not beyond 1 KB. So there you can't write a program beyond 1 KB. Right? Somehow your logic must fit in 1 KB. It's very difficult for any programmer. But that's not an issue now. Why it is not an issue? Virtual memory is there. If it is going beyond 1 KB, you can always fit it using the virtual memory. So programming task is very simple. The other one is you can always share the code as well as address space with the others. So what's the meaning of that is suppose see let me go down here. Okay, suppose one page is mapped here. Okay, this page. This is used by one program. Some other program can also use the same to read the content from here. The same physical location is mapped by other program. Same physical location is used by the other. So because you have to just map that, so same frame is shared among them. So many process can directly use it. So it is that advantage. Always you can use it. The next one is because you are not loading the entire program into the memory, more programs can be loaded. When you load more program, what will happen? CPU utilization definitely increases, throughput increases, turnaround time decreases, and the response time also decreases because more programs are there. Next one is less input output is required. So during the swapping, we have already seen that the entire program is swapped to the disk or it is written out from the disk. Now instead of writing the entire program and reading it back, we can read only part of the program that is really required and then write back if it is required. So because we are reading only a part of the program, not all the entire program, only what is required, we can definitely improve upon the input output. The other thing about this particular other benefit about the virtual memory is it is more efficient in creating the process using virtual memory. There are two ways in which virtual memory can be implemented. One using the paging, the other one using the segmentation. So if you are using paging, it is called as demand paging. If you are using segmentation, we call that as a demand segmentation. So let's look at what is a demand paging. Now this is similar to the paging with the swapping. So idea you are already familiar. You can page as well as you can swap the content. Okay. So in this particular system, the entire process will or the entire program will remain in the secondary storage. Okay. When the program executes, the pages, the corresponding pages are swapped into the memory, and this is done using a special type of swapper that is called as a lazy swapper. So why do we call it as a lazy swapper is because this particular swapper will not load the entire program into the memory, rather it will load only those pages which are required. So we know very well, we divide the program into pages and these pages are loaded into the frames. So only those pages which are really required for the execution, the lazy swapper, that is why you call it as lazy. It is a very lazy. It will not load the entire program. It will load what is required only. So you know very well, these lazy guys, what they do is they do what is required. They don't go beyond that. So similarly, this particular swapper will load what is really required. It will not load the entire thing. Okay. The When we talk about this virtual memory implementation, so virtual memory contains a pager. So this is, you know very well, how do we handle the virtual memory? Virtual memory can be handled using the pager. So pager loads the page that is required. So that's a usual way how we go about paging. So in the paging, what happens? The page is not the pager will load that thing. Okay. The only thing is, when the program gets loaded, the swapper, the program that is getting swapped in, we guess which page is really required. Only those pages we will load it. So in general, when we talk about the pager, what the pager is generally doing, it will load all the pages. Here we don't try to load all the pages. We try to guess which pages are required, and only those pages are getting loaded. Now, how can we guess? The easiest way is the locality of reference. I told you. What is the meaning of saying locality of reference? If your code is executing here, okay, the page near to that, you just take it and load it, because most likely that you are going to use the content of that particular page. You may not try to go to a page which is extremely at the other side, unless and otherwise some reason is there, like you call a function which will jump to the other place and then load it. That's a different issue. Okay, so instead of swapping the whole process, it brings in only the required pages. Okay, so what's the advantage there? So if you try to load the entire page, it's going to take a lot of effort. Why a lot of effort? It's an input output operation, and you know very well, input output operations are always slower. So instead of loading the entire page, you load what is really required. Okay, and the other part is, you will not anyhow. So suppose if you load the entire program, when you are starting the program, only starting part of the program will work, the ending program may not work. Okay, so there is no point in loading them into the memory, because you are not going to use it now. Maybe later you may use it. Okay, so this decreases the time for swapping in the process. So what is being done over in the virtual implementation is, only those pages which are required, okay, only those pages which are required, only they are brought into the memory. And when you are swapping out, only these which were swapped in are being taken out. Instead of loading the entire program, very big chunk of pages, you just load what is required. So this way you are reducing the time on input output. And you know very well, anything that is saved in the input output is a huge saving, because input output is one of the costliest thing that you can ever do in a program, because input any peripheral for that matter, any input device for that matter, or any output device for that matter, cannot compete with the speed of the CPU, and input output operations are always slower. If you are able to reduce them, then your program will run automatically faster. Okay, however, there is no magic as such. So you can't, I told you that you can swap in something, you can swap out to something, well and good. But it is not going to happen in without any effort. You need additional hardware for doing that thing. One of the hardware that is required is how to get the pages into there, and how do you track that the page really is there in the memory. For that, we use a scheme called as a valid invalid bit scheme. So it's a very simple idea. Whenever your program is executing, whenever your program says a particular page is required, so I want a particular page in the physical memory. Now here I told you there is a mapping. Okay, so in this mapping, you just check whether that page is already there or it is not there. If it is there, already loaded in the memory, you mark that, okay, this particular says I want page number 1. If the page number 1 is already there, you mark the bit as it is valid. If the program says I want page number 40, and if the page number 40 is not there, the page number 40 is not there, you mark it as invalid. So with every entry, of the page in the mapping, you mark whether it is a valid or invalid. So what is a valid bit or a bit value that is valid? That means to say that associative page is legal and it is in the memory. What is the meaning of saying legal? Legal means that page may be there in the memory, but it is not belonging to your process. Somebody else, you know very well, the operating system is not only running your program, it is running many other programs. So that page may be there, something may be there in that memory location, but it is not of your program. It is somewhere somebody else's program is there, because for operating system it is not just running your program, it has to run other program also. So or it is not, that is this is going to create an exception, because you are trying to read somebody else memory location. But the other one is, you, let's say, let me give you a simple example. Your program is there and your program says I want the page number 40. So there is a mapping here, and this is the physical memory where your program should be there. So the mapping says, it says in the location 5, let's say in the location 5, page number 40 must be there. Okay, page number 40 must be there. But as of now, the page number 6 or 7 or anything, so let's say page number 8, okay, page number 8 is already there. Page number 8 is occupying the frame 5. It's already there. Some frame is already there. Remember, physical memory, I can place anything there. So if 40 is not there, something else is there. It is not your frame, but somebody else's frame is there. So it is illegal. It's not your frame. It is someone else's frame. So you need to move it out. So valid means it is there. Your page is valid. It is there. Invalid means it is not a valid. Okay, it's not either. There are two things. Either you are trying to search for a memory which does not exist, address space or logical address space itself is wrong, or it is not existing in the memory. Someone else page may be there. So in any case, it is invalid. Okay. How does this particular process work? So initially you set entire virtual page, all the entries in the the page table as invalid, because no pages are loaded. As and when pages are brought in, mark them as valid. Okay. So if the page is not currently there in the memory, you just mark it as invalid. If you have swapped out for some reason, mark them as invalid. So let's look at a simple example over here. Okay. Now the content A is there. So you notice that the content A is there. Okay, where is that? So this is the page 0. So page 0 content A is already loaded from the disk. Content is already loaded. It is already there. Okay. So if you look at here, if the process says I want to read that page. Okay. So where is this page? So this page, location 0. You go here. So where is it? It is in the frame 4. So this is the frame 4. You notice that it is there in the frame 4. It is here. So it's there in this place and it is there in this place. So this, it is there here. Okay. Now is it valid? Next question comes. Is it valid? Yes, it is valid. Why? Because valid bit is valid. What about B? Suppose if you go to the B, suppose if the program says the content of B, so where is B? It is 1. You go here to 1. Okay, what you notice? You go here, it is not loaded. And what does it says? This is invalid. Nothing is loaded. It's not there. So what you are supposed to do in this case? Suppose if you load this B here in the location 2, if you load this B here in the location 2, you just mark it as 2. It is available in 2 and make it as valid, saying that it is valid. Okay, so as simple as that. What about 5 here? So 5, look at here, 5. So 5 is there, 5. Okay, so you go here, 5. Where is it? It is in the 9. So in the physical memory, frame is 5. Is it valid? Yes, it is valid. So you go and read the content. So if it is there, you read it. If it's not there, you get it and then read it. Okay, now what happens if the page is not there? So this is what happens. So I told you, when I try to read B, so where is B? B is there in the 1. In the 1, this page is not there. How do you tell the operating system that this page is not there? For that, you have to generate a interrupt. You have to interrupt the operating system and say that, see, I wanted that page, it is not there. That frame is not there. Get that frame, read it and get it back. Okay. When the process executes and accesses the page, if the page is there in the memory, there is no problem. Suppose when the process goes and searches for the page, and if that page is not there in the memory, then the page has to be brought into the memory first, and then the execution continues. So you try to read something, it is not there in the memory, first get it into the memory and then start reading it. So this somehow you have to tell the operating system that this has occurred, and this can be done using page fault trap. So you generate a trap and tell the operating system that there is something wrong, I am not able to read that page. Now what's the meaning of saying page fault is the operating system has not brought that page into the memory. Page fault does not mean that it is an invalid address or an illegal memory reference. Remember, illegal means you are trying to read somebody else's memory location. So program 1 tries to read the memory location of program 2, which is illegal unless the memory is being shared. Suppose if the memory is not shared, program 1 tries to read the content of or the memory location of program 2, it is illegal. Operating system immediately terminates that program, says that this is completely illegal. Now that's a different issue. Here what is the issue? Here the issue is you are reading a valid page, but the operating system is lazy, it has not brought that page. So you just go and knock the operating system and say, see, I wanted that page, you have not brought it, get the page so that I can continue. So that is what is a page fault. So how does the page fault algorithm works? So first of all, when you how does operating system handles the page fault? So when if you go to the operating system and write a complaint saying that I wanted to read that page number 5, page number 5 is not there, I want nothing is available. So in that case, what the operating system will do? First, the operating system will come to your process control block. So it will come to the processors. That is the process control block here. This is PCB, to check whether whatever you are asking, is it valid, is it internally, is it valid. So it checks the internal table of the processor to determine whether such a reference is valid, whether your program is allowed to read that memory access or not. If it is not valid, then it will terminate the program, because this is illegal. You are trying to read somebody else's memory location, means it is illegal. Suppose if it is a valid reference, so this page is your page, your programs or your processes page, but it is not there in the memory, then it will load that, read the page. So what it will do, it will check the memory. See, remember, loading means it has to put that thing in somewhere in the physical memory. So it will check the physical memory. Wherever the free space is there, it can put it there. If the free space is not there, it has to make a free space and then put it. So first, it will try to find a free frame. So from the free frame list, then it will go to the disk and say, I want that page to be read and put it into that memory location. Go ahead and do that. So disk will faithfully read it and put the content into the frame, and once it completes, it comes to the operating system and says, my work is done, you told me to put the page into that frame, I have done that thing. So once it is done, it will go to the mapping table, and it will say that this particular page has been mapped. It will come back to the your program or your process and says, okay, sorry for the interruption, I brought that page there, now you can continue with your work. So this is how it really works. So there are extreme cases are there. So what is this extreme case? Extreme case is when operating system does not load anything. Remember in the example that I have just shown you here, okay, I think I missed one diagram there. Okay, if in the example that I have, operating system has loaded few of the pages. If you notice here, few pages were loaded, but not all the pages were loaded. So if the operating system is very lazy, what it will do is it will not load any page. It will say that I won't load any page. So in that case, what's going to happen? In that case, when your program starts, for the first instruction itself, it will generate a page fault. By when the CPU says, okay, what's your next, give me the program counter, read the first instruction, it goes to the memory and it is not there. So you knock the operating system and say, get the page first. Operating system gets the first page. Okay, you got the first page. Now first page may require the second page. So when the first page is completed, you go again, ask the operating system, get the second page, it will get. So that means whenever you make a demand, then only the operating system will load. So when the program process starts, your process starts, operating system will not load anything. Just it will load the header, that's all. Your program header is only loaded. No content, no instructions are loaded. Whenever your program says get the page, then only it will load. This is called as pure loading, pure demand paging. So what is pure demand paging? Never bring in a page until it is required. So until somebody says do the work, you don't do it. So you, in other words, okay, so operating system will not get any page. Okay, now this works fine because of the locality of reference. We know very well when we are in the page 1, you may next you may try to load the page 2 and so on. You may not jump, so it works fine with that. And as I've already told you, there is a hardware support that is required for this particular thing to happen. One of them is the page table. I told you page table contains the whether the particular page is valid or invalid. For that we need that. Next one is we require a secondary storage wherein the pages can be stored. Generally this is a disk that in today's world it is a disk that we are using. So this device where your pages are stored, that's called as swap device. And the section where the disk writes that thing, that is called as a swap page. Now you may be thinking, okay, is it really there, sir, in the operating system? So I am using Windows, do I get the virtual memory? The answer for that is Windows also uses virtual memory. So you may ask them, can I find it on Windows? How can I find the virtual memory in Windows? Now if at all you are really interested, just go to the settings in Windows and then just search for performance. Okay, under performance you may get something like adjust appearance and performance of Windows. So you do that. So you will be given this kind of performance option. You go to the advanced option and you notice in the advanced option actually it is doing a process scheduling. And what does it says? It says something about this virtual memory. So a paging file in this area, so how much it is taking? Nearly 4000 MB space it is taking. Okay, that much of a memory, nearly 4G the data is it is taking 4 GB of data it is taking, just to give you an idea. So if you want additional virtual space, you can go and change it. So when you try to change it, generally Windows says I will manage it on my own. Virtual memory I will manage it, you don't bother about me. But because I want to demonstrate to you, I will say that no, I want to manage. So the Windows says you have 3 partitions, C, D and E partitions are there. I am only taking memory in the C drive. I am not using virtual memory in the D drive. Only C drive I am using it. How much? It says you have 160 MB 16 160 GB memory is there. So out of that, okay, I am using minimum is 16 MB, maximum is 4352 MB, and recommended is this one. If at all you want to change it, you can always send click on custom and then set the initial and maximum size. If at all you want to do it, if you really know what you're doing, you do it. Otherwise, just allow the Windows to manage it. I will not click OK. I will click cancel, and also I will click cancel. So this, you notice that Windows also uses that. So virtual memory is not just a theoretical thing which is there on your machine. It's there in your Windows. You can always find the virtual memory. Okay. So again, if you really want to know more about it, please refer the Galvin's book on operating system. Thank you for your interest. We'll meet again in the next class.